Somewhere along a stream bank in Yellowstone, right now, someone kneels to fill a water bottle. Beside it grows a plant with a root that looks like something pulled from a garden. It has already killed people in this exact park, and it is still growing here today. That plant is water hemlock, the most violently toxic plant in North America. One bite of the root can end in seizures within minutes. There is no antidote. There is, supposedly, one detail that separates a safe root from a lethal one. A single vein in the leaf running to a notch instead of a point. One line on one leaf stands between the person at that stream and a fatal mistake. So, the real question isn't whether this happened before, it's whether the rule meant to stop it actually works, or only looks like it does, until someone finds out the hard way. Before we get into why that rule keeps failing, subscribe now if you want more investigations into the plants hiding in plain sight across America. The United States Department of Agriculture does not soften its language on this plant. Its Agricultural Research Service, operating out of a poisonous plant research laboratory in Logan, Utah, describes water hemlock plainly as the most violently toxic plant that grows in North America. That is not a phrase from a foraging blog trying to sound dramatic. It is a federal research designation built on decades of documented poisonings in livestock and in people, and it sits at the top of a very long list of plants this same laboratory has spent generations studying. Water hemlock belongs to the carrot family, the same family that gives us the vegetables sitting in a supermarket bin. Carrots, parsnips, celery, parsley. Nearly every plant in that family shares the same basic architecture: a hollow or ridged stem, small white flowers gathered into flat, umbrella-shaped clusters, and often a thickened, edible-looking root. In the wild, that same family includes yampa, a small tuberous root that has been gathered and eaten across the American West for generations, valued by indigenous communities long before Yellowstone was ever declared a park, and still sought out today by wild food foragers who genuinely know what they are doing. Water hemlock's root can look enough like a yampa root, or a wild carrot, or a wild parsnip to fool someone who is confident in their identification skills. And confidence on its own has never been a reliable filter for danger. Yampa itself, the plant most often named in these Yellowstone cases, is no obscure footnote. It was a staple food for the Blackfoot, the Northern Paiute, the Cheyenne, the Comanche, and the Nez Perce, prized enough that one of the major Comanche divisions took its name from the root. Members of the Lewis and Clark expedition documented indigenous foragers gathering roots from this same plant family during their 1806 journey through present-day Idaho, though which exact species was collected remains debated among historians who have studied the expedition's botanical records. The plant itself grows low and slender, a foot to 3 feet tall, with narrow, grass-like leaves divided into thin segments, and a small, thumb-sized root often compared to an almond. Nothing like the thick, pale tuber water hemlock produces. The danger was never that yampa is hard to identify correctly. It is that a root pulled from the ground, without the telltale leaves still attached, can be genuinely difficult to tell apart from the plant that killed Charles Phillips. Yellowstone itself puts the scale of that danger into perspective. Park botanists have cataloged 1,491 native plant species inside the park's boundaries. Of those, exactly 2 are capable of killing a person outright, even in small quantities. Water hemlock is one. Meadow death commas is the other. Everything else in that enormous inventory, every wildflower, every shrub, every grass along every trail, falls short of that threshold. Out of nearly 1,500 options, this is the one the park's own naturalists single out as demanding absolute caution. And water hemlock does not hide in some remote, hard-to-reach corner of the park. It grows along stream banks, in wet meadows, at the edges of the exact water sources that backcountry hikers and campers are naturally drawn to for a place to fill a bottle or pitch a tent. The plant needs consistently moist ground to survive, which means the conditions that make a spot feel like a good place to stop are frequently the same conditions this plant depends on to grow. Physically, water hemlock is not a small or easily overlooked plant. It grows as an erect, hairless perennial, reaching 3 to 6 feet in height, tall enough to stand at chest level next to an adult. Its stem is hollow, often streaked or spotted with purple, and at its base sits a cluster of thick, tuberous roots. the exact feature that invites comparison to a bundle of wild carrots or parsnips. Every part of the plant carries the toxin, the roots most of all, but the leaves and stems as well, which means even careful handling carries some risk, not just eating. This is the boundary the field guides and the rangers in the survival manuals hand down as settled fact. Know the vein, know the notch, and you are safe. It is treated as a hard, dependable line, not a loose suggestion open to interpretation. And this rule doesn't only fail in some distant sealed-off decade. It has failed before, more than once, and it fails now the same way it always has. In 1927, according to Lee Whittlesey's History of the Park, Death in Yellowstone, a ranger naturalist named Charles Phillips mistook the root for camas, ate it along with a winter keeper and his wife, and was found dead in his cabin near Old Faithful the following evening. The winter keeper and his wife, who ate less, were violently sick through the night but survived. In 1985, a backcountry camper made the same mistake with the same plant, believing its root was yampa. A companion spat it out at the taste and survived. The camper did not stop there, went into convulsions, and died despite hours of rescue efforts from park rangers. Two names, decades apart, both undone the same way, judging a root without ever checking the leaf. None of this is sealed away in an old book. Reporting from Cowboy State Daily in 2025, drawing on current park sources, confirms that water hemlock has caused at least 2 documented fatalities inside Yellowstone, and that park staff continue to actively warn visitors about it today. That warning exists right alongside every modern tool a hiker might carry into the backcountry. Trail apps, satellite messengers, detailed plant identification guides available on almost every phone. None of it has retired the warning. It has simply had to keep being repeated, generation after generation, to people who assume modern tools make this kind of mistake obsolete. Rangers today back that warning with signage at trailheads and visitor centers, and with laminated plant identification cards posted at exactly the kind of wet, streamside ground where this plant grows. The message printed on that signage is the same one that failed Charles Phillips in 1927 and failed the camper in 1985. Know the vein, know the notch. It is repeated now with better maps and more information than either man ever had, and the plant has not gotten any easier to identify by root alone in the meantime. Current park sources cited by Cowboy State Daily point to an additional, above-ground marker rangers now emphasize in that signage. Small purple or reddish-brown blotches on the plant's hollow stem, described by one park source as practically a built-in warning label, distinct from the smooth, unspotted stem of its edible look-alike, Queen Anne's lace. Combined with the serrated leaf veins and the white flower umbels, the plant is described as one that, above ground, essentially identifies itself. The warning rangers repeat today is not that water hemlock is subtle. It is that none of these visible clues matter to someone who has already stopped looking at anything above the dirt line. Yellowstone's own record-keeping treats water hemlock as something close to a singular threat among plants. The park is also home to several deadly poisonous mushroom species, among them the death cap and the destroying angel. Yet those fungal deaths remain rare and scattered by comparison. Water hemlock is different. It is the plant the park's own current safety messaging returns to again and again, not because it is rare, but because it keeps finding new people today, willing in good faith to trust their own judgment about it. So, the harder question isn't just why this happened before, it's why an active, well-publicized warning campaign, right now, still isn't enough to fully stop it. To understand that, you have to look at what water hemlock actually does inside the body once it is swallowed, because the mechanism explains something the identification rule alone can't. The toxin responsible is called cicutoxin, first chemically identified by researchers in the 1950s, and it belongs to a class of compounds known as C17 polyacetylenes. It is concentrated most heavily in the plant's tuberous root, the same part people mistake for yampa or wild carrot or parsnip, and it is present there in a straw-colored liquid that sits inside small internal chambers, released the moment the root is cut, bitten, or crushed. In the year 2000, a team of researchers led by UY studied cicutoxin's effect directly on brain tissue and found that it acts as what toxicologists call a non-competitive antagonist at GABA-A receptors. GABA is the brain's primary braking system. the neurotransmitter responsible for calming neural activity down after it fires. When cicutoxin blocks that receptor, the brake simply stops functioning. Neurons that should be quieting down keep firing instead, cascading into each other, and the result is exactly what witnesses described in both Phillips and the 1985 camper. Seizures that begin within roughly 15 minutes to a few hours of ingestion, following an initial wave of nausea and salivation, and ending, in fatal cases, in respiratory paralysis. The body's own breathing simply overwhelmed by uncontrolled nervous system activity it can no longer regulate. The progression itself is not a single dramatic moment, but a cascade. Toxicology literature describes an early phase of heavy salivation and muscle tremors before the body moves into what clinicians call a grand mal seizure, uncontrolled convulsions that can recur in waves rather than as one continuous event. The tuberous root, the plant's storage organ, holds the toxin at its highest concentration by a wide margin, denser there than in the stem, leaves, or flowers above ground. A later study, published in 2015, examined cicutoxin concentrations across water hemlock populations throughout the western United States, sampling tubers from multiple sites, and found real, measurable variation from one population to another, and even from one tuber to the next within the same patch. This is not a plant with a single, predictable dose of danger baked into every root. Two tubers that look identical, pulled from the same stretch of stream bank, can carry meaningfully different amounts of toxin, which means a person's past experience with the plant, if they somehow survived a small exposure once without symptoms, tells them almost nothing reliable about what the next root or even the next bite will do. There is no antidote. Treatment, then and now, is almost entirely supportive, controlling seizures, protecting the airway, and waiting to see whether the body survives the initial chemical storm long enough for the toxin to clear on its own. That was as true for the rangers working on the 1985 camper for hours as it would be for a hospital team today. Water hemlock does not give responders a chemical to counteract, only a window of time to manage the damage as it happens. The same toxin is responsible for a long history of livestock deaths as well, cattle and sheep grazing too close to a stream bank, which is part of why the USDA's Poisonous Plant Laboratory in Logan has studied this species for so long in the first place. Originally as an agricultural problem, before its relevance to human foragers became just as well documented. But the detail that matters most for Phillips and for the camper in 1985, and very likely for the people this same warning is aimed at right now, is simpler than any laboratory finding. The one diagnostic feature that is supposed to separate water hemlock from its safe relatives, that single vein running to a notch rather than out to a point, sits on the leaf, not on the root. In nearly every documented Yellowstone case, the person was not examining a leaf at the moment of decision. They were digging up a root, judging it by shape, by feel, maybe by smell, the same way anyone might judge a carrot pulled from a garden bed. The rule was never actually broken in the way people usually imagine a rule being broken. It was simply never in the room when the decision got made. That solves part of the mystery. It does not solve all of it. Knowing that the identification rule depends on a part of the plant most root foragers never think to check still does not fully explain why a trained park naturalist, someone whose entire job depended on exactly this kind of caution, skipped that step in 1927, in the middle of winter, with no one urgently pressuring him to decide fast. For that, you have to look past the plant itself and toward the people making the call. There are two explanations sitting in tension here, and neither one is comfortable enough on its own to fully win the argument. The first is the clean explanation, the one rooted entirely in botany. Water hemlock belongs to a family of plants that has produced some of humanity's most trusted food crops: carrots, celery, parsley, parsnip, alongside genuinely valued wild foods like yampa. Convergent structure within that family, similar umbrella-shaped flower clusters, similar tuberous roots, similar preference for growing near water, means the resemblance between the deadly plant and the edible ones around it is not a coincidence or a rare fluke of one unlucky specimen. It is closer to a structural inevitability of the plant family itself, repeating in every region where these species grow side by side. Under this explanation, Misidentification is less a personal failure and more a predictable outcome of botany that has been quietly repeating for as long as people have foraged in this part of the world. The second explanation is muddier, and it centers on people rather than plants. It points to a pattern of relying on a single quick heuristic in the moment: taste, root shape, a half-remembered image of what yampa is supposed to look like, instead of walking through a full identification process that includes the leaves. It points to the conditions that push people toward that shortcut in the first place: hunger, isolation, the accumulated confidence that comes from years spent outdoors without incident, and the genuine, well-founded tradition of yampa foraging itself. A tradition that is entirely safe in the hands of someone who has been taught its full detail, and considerably less safe in the hands of someone who has absorbed only the general shape of it secondhand. That second explanation has not gotten easier to manage with time either. Modern wild food foraging has grown into something closer to a movement, with guidebooks, phone apps, and online communities that share tips, photos, and identification shortcuts at a scale that simply did not exist in Phillips's era, or even in 1985. Some of that shared knowledge is careful and accurate. Some of it compresses a genuinely complex identification process into a quick visual comparison that leaves out exactly the kind of detail, like checking a leaf vein instead of a root shape, that actually matters. Easier access to information does not automatically mean more careful information, and a plant that has been fooling people since before any of these tools existed is not especially impressed by a phone in someone's pocket. Peer-reviewed. Testing of smartphone plant identification apps, evaluating their ability to tell toxic and edible species apart, found they cannot be relied on for that purpose at all, with accuracy that varied sharply from one app to the next, and outright failures on some of the exact toxic lookalikes foragers actually encounter. The researchers behind that work concluded plainly that these tools cannot yet be used to safely identify what is edible in the wild. A shortcut that fails quietly, offering a confident-sounding answer instead of an honest one, may be more dangerous than no shortcut at all, since it replaces uncertainty with a false sense of it. Neither explanation cleanly wins, because on close inspection they are not really separate at all. The plant's resemblance to yampa is real enough to deceive a genuinely careful person, not just a careless one. It does not need to be a perfect disguise to be a lethal one, only good enough to meet ordinary human confidence roughly halfway. The disagreement among the people who study this, botanists pointing toward the plant's biology, safety researchers pointing toward human behavior in the field, is not really a sign that no one has figured this out yet. It may simply be an honest reflection of a danger built out of two ingredients at once, in proportions nobody has ever been able to fully separate or measure. Even the yampa tradition itself sits awkwardly inside this tension. It is not a myth or a careless folk practice. It is a real, sustainable food source, with a long, documented history, one that requires exactly the kind of full plant knowledge, root and stem and leaf and flowering seasoned together, that turns identification from a guess into something closer to certainty. The danger was never in the existence of that knowledge. It was in how easily an outline of it, stripped down to a shape and a memory, can travel from one generation or one internet post to the next, losing the one detail that mattered most along the way. Which brings the question back to where it actually started. Not at Old Faithful in 1927, but at the stream bank where this began. Someone crouched at the water's edge, right now, filling a bottle, glancing at a plant that looks close enough to something safe to eat. Charles Phillips is still remembered in the park, in a small thermal feature near Norris, named Phillips Cauldron, a quiet, mostly forgotten marker of what happened to him. But that marker is a historical footnote, not the reason any of this still matters. What actually happened to Phillips, and to the camper in 1985, was never really a failure of intelligence in some rare, isolated way. Each of them looked at a root, thought of a food they already trusted, and made the same kind of quick judgment call any of us make dozens of times a day without consequence. Park staff are still, in effect, warning visitors against that exact instinct today, with better maps, better signage, and more information than either man ever had. So maybe the honest answer is that the boundary was never really written into the leaf at all. The vein and the notch are real and accurate, and have never once failed as a piece of botany, but they only function as a boundary if someone stops, in the moment of deciding a plant is safe enough to eat, and actually goes and looks. The real line was never fully in the plant. It was in that pause, the half-second of certainty, right before someone decides they already know enough. Nothing about the plant has changed since 1927. Its chemistry is the same, its resemblance to yampa and wild carrot is the same, and the leaf vein that could have told Phillips the truth still runs to the same notch it always has. What has changed is only the number of warnings posted around it, and the number of people who still walk past those warnings toward the water. Somewhere along a stream bank in Yellowstone, right now, someone crouches down to refill a bottle, glances at a plant with a thick, pale root, and decides, in half a second, that it looks close enough to something they already know. The water keeps moving, the plant keeps growing, and the decision, every time, still comes down to that one unchecked leaf.